And then before I get started, did anyone have any like major questions they needed to start off with? Okay. So then first of all, the first thing I just want to go over, I just want to go over a few key things about chapter 14, and then we'll get into a few practice problems. So first things first, this part of chapter 14 really was just primarily focusing on the reaction mechanisms, right? So we went over these in like recitation 4, and you guys are going over them in lecture, but I just want to touch on a few key things here. First of all, just remember that these mechanisms are split up into different reactions to add up to one like overall reaction. We can describe these individual reactions known as elementary reactions um, with these terms bimolecular, monomolecular, and termolecular. Big thing just kind of emphasize here is just the fact. Yeah, we'll go over some of the quadratic equations when we get to chapter 15. Um, so you'll see that these kind of are what describe these elementary reactions. Remember that this has to do with the number of reactants that you have. If you have two combining, they're bimolecular. If you have kind of one that's just decomposing into other products, that's going to be monomolecular. And then if you have three, that's termolecular. The one thing I want to emphasize with this one is that it's not about the number of like different like species that you have, it's about the number of particles. So this certain one in particular has like two I mean, I just chose random letters to represent the reagents, two F's and a G that all combine to give you your product of H and B. So does anyone have any questions about those terms? Because that's the only like really confusing aspect of it. Okay. So then remember with elementary reactions, when you're writing out your rate laws, remember that these give you the order just from their coefficient. Remember, intermediates are produced in one step and then consumed in another, and catalysts are initially consumed and then reproduced in the product. Can do you all remember what the difference between a heterogeneous and a homogeneous catalyst is? Okay, so just to kind of recap, remember that a heterogeneous catalyst is a catalyst in that is a different phase than the rest of the reactants that it's working with. While homogeneous, it's the same phase. So kind of an example here, if you have two gaseous components, let's say they're producing C, and the catalyst that you're going to add is like solid iron. That is a heterogeneous catalyst because it is a solid while these are gas. And this one, best example I can give you is like an acid. So let's say you have, sorry, I'm just trying to think something off the top of my head. This is a type of organic molecule. It's called an ester. If you add an acid to it, you will be able to produce a product. A product. I don't want to confuse you all with a bunch of organic chemistry, but my main point here is this is aqueous, and so is this, and that makes this a homogeneous catalyst. Do I have any questions about that?
So
No.
like how would you be able to tell on like a exothermic or endothermic reaction like if that catalyst is homogeneous or heterogeneous? Or would you only
If you
determine it by the like actual reaction?
if they're gonna ask you to find to identify a catalyst as homogeneous or heterogeneous, they have to give you the reaction equation. You have to be able
Okay.
to know you have to be able to know what the phases are for you to determine that. Any other questions? Okay. So that's like the big part of chapter 14. Obviously, it doesn't make up a whole lot of this chapter. I do have a few practice problems I want to go over with you guys. So, and I can give you guys like a minute or two to kind of try this on your own. But this is the first question I want you guys to do. This is just a basic reaction mechanism, kind of just made with like simple letters. They tend to do that a lot. They don't use like actual chemicals for some reason. I'm not sure. But go ahead and try to find the rate law for this. I I would almost bet money that you guys are going to have to do this tomorrow, and then we will go over it step by step. And I'm actually going to widen it because I actually have two problems here. Both of these, I need you to find the rate laws. Okay. So I'll give you guys a few minutes to do that, and then we'll go over it. All right, let's go ahead and go over it. I'm actually going to start off with number two, because number two should have been really easy. So, when you're looking at a reaction mechanism and they ask you for the rate law, first thing you should check is your first step a slow step? In this case, it is. If it is, your job is really easy because all you have to do is put down that rate is equal to K times those reactants. And remember, the orders are determined by the coefficients, so they are both 1. That's kind of the simple aspect of it. Remember that slow step is that rate determining step, so that's why that determines the rate law. And the rest of it doesn't have any effect on it. Does anyone have any questions about that? All right, let's go through this one. So this one has a slow step in the second step. So obviously this is a little bit more complicated. So if you have a slow step in the second step, first things first, first of all, you always have to have that equilibrium in the first step. That's always going to be given to you. So write forward and reverse rate laws.
I have a question. Will there be equations where it'll be only forward, or those types of questions won't be given?
Like in the first step?
Yeah.
Yeah, you will not be asked that.
Okay, thanks.
For all reaction mechanisms, you have to be given an equilibrium. So, as I hope you all have picked up by now, forward and reverse reactions of equilibriums are equal rate. I hope you all have that down. So, I can put these rate laws equal to one another because these are elementary reactions. Remember, we can just determine the order by the coefficient on this side. So the forward reaction is K1 times the concentration of A times the concentration of B, and the rate of the reverse is equal to K -1 times C times D. Now, because we know that these rates are equal to one another, I can set these equal to each other. And always feel free to interrupt me if you have a question. So that's what we have. So at this point, you need to identify the intermediate. So I just realized I wrote it out for that's my bad. My screen wasn't pulled down far enough. Oops. So this should be the diatomic A, and this one should be A squared. All right. So set those equal to each other. What is the intermediate here?
Just the A.
Exactly. Just the A because it's produced here and it's consumed here. So what you need to do is you need to solve this for A. So we have K1 times the diatomic A is equal to K-1 times the concentration of A. So I'm going to divide over K-1. Because at this point, it's just algebra, right? And then we take the square root of both sides. Sometimes taking the idea of taking the square root, students aren't a fan of that. It's okay. All right. Now we're going to plug in to the slow step. Okay, so for the slow step, which is your second step here, is going to be rate is equal to K2 times the concentration of A times the concentration of B. We just figured that out like we usually do. So now I'm going to plug this in for A. So I'm going to do K2 times K1 over K-1 to the 1/2 times A2 to the 1/2 times B is equal to your rate. Now, at this point, this entire thing is just going to be reduced to K. Just because remember that this is just a constant. It's just some number and we don't care what it is. So rate is equal to K times the concentration of diatomic A to the 1/2 times the concentration of B. And that will be your answer. Does anybody have any questions about how we figure that out? Sweet. So yeah, on your exam, the only kind of questions that I would expect them to ask you regarding this stuff is to identify like the stuff we talked about up here, with things being intermediates or catalysts, or maybe identifying one of these terms. Down here, I would expect that they're either going to ask you like this, just like find the rate law, or they could give you like we did one of these for practice and mechanism where they give you multiple mechanisms and ask you which one satisfies this rate law. It's the exact same format. You just need to find the rate law of each of them and figure out which one matches. Okay? Any questions? All right. I did want to talk about this real quick. So reaction mechanisms are something that always come with, sorry, when Brayden, do you mean like this? Heterogeneous versus homogeneous catalyst, it's very simple. It's just if you have all of your reactants are one phase and then your catalyst is a different phase, it's going to be heterogeneous. If it's homogeneous, they're all the same phase. The way I usually see this happen is with homogeneous catalysts, they're usually aqueous and they're usually just in a solution. And acids are a huge example because acid catalyzed reactions are like the most common thing in like organic chemistry, or base catalyst reactions. I know are in Gen Chem, but like that's something I really commonly see. With heterogeneous catalysts, it's a lot of metals. Can we go over where we got the 1/2 real quick? Sure. So that's just from taking the square root of both sides. So we started with the rate, the forward rate is equal to the reverse rate. And then I divided over K1 like this. So that got us here. And then I took the square root of both sides, which is just the same thing as being to the 1/2 power. And that's how I got here. And then just to here, it just carries over. Did that help explain that? Okay, cool. All right, so with this, first of all, identifying, which I'm just going to kind of talk through this, but please pay attention to it. It might be important. So first of all, with these reaction mechanisms, this is the one I gave the example of. Identifying certain things to be able to identify here. Here are reactants. Here are our products. I almost called reactants. This is our activation energy. This is our delta E. In this case, delta E is less than 0. Extremely less than 0. This is a very negative, this is a large energy relief, which means that this is exothermic. Okay? So, I want you guys to think about the rates of reaction here, comparing the forward and the reverse rates. And I'm also going to tell you that this is at equilibrium. So we're going to kind of play into our next part here. Would you expect that the forward or reverse rate is going to be Obviously, at equilibrium, the rates are equal. We know that. But which one of these is obviously more favored? The forward or the reverse reaction?
Is it reactants because it takes less energy?
Exactly, the forward reaction. So the forward reaction in this case has a much smaller energy barrier. Which I like to call activation energy. So there is a much smaller barrier to that reaction, which means once you hit equilibrium, it's very likely that that forward reaction is going to predominate. So if I'm telling you that that forward reaction is predominating, is Kc going to be a lot greater than 1 or a lot less than 1?
Less.
Why less? Yeah, so Braden got it in the comments, it's a lot greater. So the reason for that is if our forward reaction is predominating at equilibrium, you're going to have a lot more product. And remember, our expression for Kc is equal to the concentration of products over the concentration of reactants. So if you are going to be having a lot more products in comparison to that concentration of reactants, Kc is going to be a much larger number. Does that make sense? Or does anyone have any questions? Okay. And then for our rate constant, so essentially the rate constant is going to kind of be in kind of proportional to your activation energy, and this is something you can remember with or it's going to be inversely proportional. I'm going to, because they will give this to you on your supplemental information for your exam, where you because there's just one equation I need to point out to you guys. Actually, I'm not sure. I'm just trying to make sure they give it to you. And I'm not 100% sure if they do. Okay, never mind, they don't. So the way I would just remember this here is, you know, obviously we just talked about how that forward reaction is going to be predominant. It's going to be just because it has this lower barrier for energy. That's going to cause the rate constant in the forward reaction to be greater. Okay. Does anyone have any questions about that?
So is there like a general rule of thumb for that? Like how we can remember it? Like if this increases, and this decreases?
You mean like trend wise?
Yeah.
So, because the equation that you can usually use to relate it is this. they don't give it to you on a midterm too. But I did just want to cover it if they talk about it. It's just like kind of one of these trends. Like this is a negative value. So as this value is going to increase, like if you remember things like equation wise, you're going to see this decrease. And like it's just a way to think about it is like your rate constant is usually very characteristic of like the reaction's ability to surpass energy barriers and proceed to the products. That's why you see it be affected by temperature, right? But we always talk about how rate constant is not affected by concentrations. That is the other part of the rate law. But this K value is going to be affected by these kind of energy barriers that the reaction has to go through. So in this case, it would be temperature that would affect it or activation energy. Okay, so Braden asked a question. It's a really good question. Braden, I'm talking about the rate constants, not the rates of reaction. The rates are your question is correct in the sense that the forward and reverse reaction rates are equal. So I'll summarize this here. So at equilibrium, rate constants can differ based on I'll rewrite that as based on activation energy, because I'm going to consider that the equilibrium, the forward and the reverse are happening at the same temperature. And then just to kind of summarize that trend, like Ella was asking, as that activation energy is going to increase, K is going to decrease. If EA decreases, K is going to increase. But rate, I'm going to put this in all caps, rates are always equal. And this usually has something to do with the fact that the reactants and products aren't, and this is the reason actually that reactants and products aren't the same concentration at equilibrium, right? Like while their rate laws are equal to one another, the Ks and the concentrations are not necessarily. What questions do we have about that? Okay, cool. All right. Does anyone have any questions about this? Otherwise, we're going to move on to chapter 15, which I know is like the reason a majority of you are probably here. Sure, I can send it. I'll also post this too, since I'm recording it. Okay, let's go on to chapter 15. So for the kind of reminders, I really just want to go over a few things here. So first things first, just a general reminder, because this is such easy points on the exam that if you miss it, it will personally hurt me. When you're writing up KC expressions, only aqueous or only gaseous reactants or products are included. If there is a solid, it is not included in the expression. Do not put it in there. If you have a solid in your KC expression, your question is instantly wrong. So, because I promise they'll do it. They will put on, it'll ask you to write out the KC equation, and every single time it has a metal solid in it. That's my bet. I'll bet my money on that. There's going to be a metal solid, and they will try to get you to put it into the reactant equation, and you will not do it. So, do not do that. Le Chatelier's principle is the one more conceptual thing that they really hit on in equilibrium. After that, it's a lot more math. And I just want to go over this just to make sure we're kind of on the same page. So concentrations to me is the easiest. If you're going to increase the concentration of something, you're going to shift to consume it. If you remove the concentration of something, you're going to shift to reproduce it. That one to me seems to be pretty simple. The one we were struggling on in class was pressure and volume. So with volume, remember that if we're decreasing the volume of the container, you are going to shift to produce less moles. So in this example I gave of molecular chloride to monatomic chloride, decreasing the volume, it's going to shift left to produce less moles of chloride. It's producing 1 instead of 2. However, if you increase the volume, you're going to shift right to produce more moles. Now, I want to think about this a little bit more from a conceptual standpoint, just so we really understand like why this happens. So let's say you're in a container and we're here and we have just, dichloride and like monatomic chloride, and they're just like floating around and they're in equilibrium. So now let's say I increase the volume of the container. And at that very instant, we have the same number of molecules. Now, we've already talked that we're shifting right. We're going to produce more of these dichlorides. But what I want you all to understand here is that when you increase the size of a container, at that instant, forward and reverse rates decrease. At that very instant, both of these reactions, both in the forward and the reverse direction, are going to decrease. And that is because when you are increasing the space in this container, the molecules become a lot farther apart from one another. Those collisions aren't happening as much, and so the reaction isn't going to happen as quickly. However, over time, it is going to be that this forward reaction is still a lot faster than that reverse one. Just simply for the fact that it kind of has a greater affinity to produce more moles in this case. And this only requires one molecule for the reaction to happen. So it's really not needed for it to combine with other molecules. But with this one, 2 chloride molecules need to come together to produce dichloride. And so that's just like kind of the conceptual aspect of it. And then Braden then asked, if we lower the volume, will it become higher at that instant? Absolutely. Because when you make it smaller, these are in really close proximity. So they shouldn't be negative, but whatever. These are in really close proximity. So they are going to be able to really interact with each other quickly. And it's the same way for the reactant, but it's going to be a lot quicker and a lot easier for those. It's going to have a lot more of an affinity to go towards the lower moles to account for that tighter space. Okay. What questions do we have on that? I know we didn't go into that detail in recitation, but I just wanted to cover that just so that we kind of have a conceptual understanding of why the Chatelier's principle works the way it works in this case, especially in terms of like rates. And then for temperature, I kind of shorthanded this So if we are endothermic, I always write it out like a concentration. That will just always be easier. If I'm endothermic and I'm increasing the temperature, I want to consume excess heat. I'm shifting right. If I decrease the temperature, I'm making it cold, I want to produce more heat, we're going left. With exothermic, it's just the complete opposite of what I just said. Do we have any questions about that? Sweet. All right, so this is a question that one of you submitted. I'm going to go ahead and just go over this with you guys. This is some of the math that I really kind of want to focus on for this section of the review session, because I know a lot of you are struggling with this. So this is actually a question from one of your recitation assignments. We didn't do it in class, so it's a good opportunity to go over it together. So they're giving us this equation. It's all gases. They give us a Kc value. And we have a few parts we need to go over here. So first part is part A. With the given information, calculate Kp. And if you guys want to screenshot this, you can, or you can go to recitation 4 activity. It's number 9. I don't believe we went over it in class, if I remember. All right, so calculate Kp. So formula Kp is equal to Kc times RT to the delta N. We are given Kc is equal to 36. R is constant. I have to sorry, I don't have my constants memorized. I believe it's 8.314.
I have a question.
Yeah.
Do we have to memorize the Kp equation?
No, it is on your supplemental information. Please go look at the supplemental information. It is on Carmen under exam 2 helpful information. I'm looking at it and it looks like all you get for formula wise is the Kp equation and the quadratic equation.
Okay, thanks.
You're welcome. So we have Kc and then R is 8.314. And then the temperature is given at 550 Kelvin. Make sure it is Kelvin. Is 8.314 is in Kelvin. It's another easy way to lose points to the delta N. So remember, delta N is it's a little confusing. Moles of product minus moles of reactant. So we have 1 mole and 1 mole. So we have 2 moles of product minus 2 moles of reactant. And that leaves us with a Kp value, which I should put a box around this, equal to the Kc value. So Kp is equal to 36. Questions we have there?
So Kc and Kp are equal?
In this case, they are equal because the moles of reactant and the moles of product are the same. If, let's say, I'm going to change it here for a second, so bear with me. I'm going to say that it was a 2Z2. I know this isn't balanced, but just bear with me. It would be 3 minus 2 because there's 3 moles of product and 2 moles of reactant. And so then you would actually just multiply all 3 of these numbers together. Does that make sense?
Yeah.
Okay, yeah, this is a special case, but it is something to know that In a case where the moles of reactant and the moles of product are equal to one another, you're going to get a Kc equal to the Kp. And if you ever given a question where they're asking about that and you're like, shit, I forgot it, go look at the equation and just use the equation. A lot of these conceptual problems can be explained by the equations. So if you like forget a trend, that's fine. Just go and check and just go check with the equation. It might help you.
So if the moles are equal on both sides, then Kc and Kp will equal each other. But if there's an uneven distribution of it, then they won't equal each other.
Exactly.
So if you used it in like the term of the equation, it'd be like technically like an exponent to 0. So that would be 0, right? And then you'd just be left with your 36.
Exactly.
Okay.
All right. Part B is asking if 0.8 moles of Az are introduced into a 2-liter container at 550 Kelvin, what will the concentration be of all of the components when the system reaches equilibrium? So, big thing here. We see that something is being introduced, and we're asking for it at equilibrium. That is indicative of an ice table. So let's get into it. So first step, we're just going to step by step here. First step, I need to find the concentration of Az because they gave you moles. Huge mistake that students make, they use moles in their ice table. I think ice table that C stands for constant or change, but you can also think that it stands for concentration if you want to really remind yourself that you need to be using concentrations. So they said 0.8 moles in 2 liters. So the concentration of Az is equal to moles over liters. So 0.8 moles over 2 liters is equal to 0.4 molar. Okay. Now, ice table. So we have 2Az is producing A2 plus Z2. All right, I, C, E. So I, initial, what are you starting with? 0.4 molar. And then both of these are starting at 0. Later, we will do one where that is not the case. I think, or I'll make sure we get one. All right, change. Minus 2x, because remember, we have a 2 coefficient here. Another big mistake. And if you guys ever can't see it, what I'm doing, let me know. Because because we have a 2 coefficient 2x, and then plus x plus x. So what is it at equilibrium? 0.4 minus 2x plus x plus x. So I got a question, would this be forward or reverse? We know this is forward because we started with 0 products. If we had more product, we would have to plug into the Kc equation to check, and I will show you that in a later problem. Step 3, find x with Kc expression. So when people do these problems, they'll oftentimes screw up something as easy as writing up the Kc expression. So please just always keep those fundamentals in the back of your head. Only aqueous, only gaseous if you're dealing with that. And coefficients and the exponent. Products over reactants. Like so. So this is going to be equal to x times x over 0.4 minus 2x squared. And then move this stuff over here. It's getting in my way. So let's simplify this a little bit further. This is equal to x squared over 0.16 minus 0.8x minus 0.8x plus 4x squared. I'm going to replace that. And that is equal to, I didn't make a math error there, did I? No, we should be good. Okay, and that is equal to our KC value of 36. So then I'm going to multiply this over here. X squared is equal to subtract over that x. To get that quadratic equation. Now from here, you're going to need to use the quadratic equation. So I'll do that in my calculator here real quick. All right, and if you do that, you will get two possible values, 0.185 and 0.218. So can one of you please tell me why one of these is wrong? Okay, so big step here, and we're actually going to put it into step 4 to find the concentration. The value of x is not necessarily your answer. And we will figure that out when we look at the concentration of AZ. If you use this value to find the concentration of AZ, you are going to get a negative number. Because if you see it's 0.4 minus 2x, 0.218 times 2 is equal to like 0.436. That's going to get you a negative concentration. Negative concentrations do not exist. This is wrong. This is always the case. Either one of the x values doesn't work because it makes a concentration negative, or one of the x values is negative itself. Okay? Any questions? Cool. So this question was asking for just all the components. So the concentration of A2 is just equal to x. So it's equal to 0.185 molar. The concentration of Z2 is equal to 0.185 molar, just because that's also equal to x. And the concentration of AZ is equal to 0.4 minus 2x, which I'm going to do my calculator here, is equal to 0.03 molar. And that is a nice table. And then we'll get to part C in a second. Any questions about that? All right. Now with part C, we need to convert this to pressure. This usually sneaks up on people because they just kind of forget about it. But it's asking for all of them. Okay. To do this, you're going to use Pfeffner. So P, and they give you the volume is 2 liters. We'll do AZ first. Is equal to N, so the number of moles. So we can do our molar mass times our volume. So 0.03 molar times 2 liters. Define these in atmospheres, 0.08206, and that temperature at 550 Kelvin. And that is going to be equal to 1.35 atm. And then partial pressure of A2 is going to be equal to the partial pressure of Z2, because remember, pressures are proportional. We know that from Henry's law, and we can just see that from the equation here because they both have the same concentration. We have 0.185 molar times 2 liters times 0.08206 times 550 Kelvin. Remember, we're doing Kelvin. Don't put Celsius into here. And then divide by 2. Sorry, I forgot to put that in here. Actually, I can just so that should be equal to 8.35 ATM. What questions do we have?
Can you explain why so the 2 liters is getting divided because it's on the bottom of the KC?
Sorry. Are you talking about this right here?
Yeah, like why in the first one is it getting multiplied and then
I forgot to. This is just Pfeffner. I skipped a step. I divided it over. Like, if you were solving for P up here, I divided over 2 under here to solve for this. Here, I just wrote it like that. I just didn't write the P, the multiply by P over here.
so you did it for okay.
I kind of just skipped a step because I forgot to do it while I was writing it. It's the same thing. These both are equivalent.
Gotcha.
Any other questions? All right. And let's go ahead. I'm going to give you guys a quick question here. This one's pretty simple, but I just want to make sure that we cover it. Calculate the KC constant for that question. All right, so this one's pretty easy. I just wanted to go over this because in new directions, they're going to tell you it's at equilibrium. Some students see that and then they start doing ice tables. Don't do that. Kc, this is very easy. Remember our Kc constant has HCl squared. These are all aqueous, or I guess gaseous. That top one is squared, and then in the bottom, we just have the concentration of H2 and Cl2. So this is just equal to 0.27 molar or 0.5 molar times 0.48 molar. Square that. And then you can run that calculation. To get that. Any questions on how to do that? Cool, good. Very foundational concept there. Just wanted to make sure that we were on the same page with that. All right. Again, with this one, I put this one in here just because I want to make sure that you all were aware of it. This is something that's very forgotten. Like just working through this, like when we have to manipulate reactants to get to a final reaction. I hope all of you remember that. I just want to make sure that we're kind of aware of the rules. I'm going to write them out here. When you flip the equation, you invert your Kc. If you multiply coefficients by a constant, I'm going to call my constant B. Kc is equal to B times Kc. Very simple. So here we flipped the reaction and we multiplied all of the coefficients by 4. So this Kc is going to be equal, I'm going to call this Kb, is equal to Kb, which I just made that. Okay, no, we're not going to call it Kb. That's actually something else important. We're going to call it Ks. I made it up. Ks is going to be to the -4th power. Negative because we flipped. 4 because we multiplied by 4 for coefficients. Yes? So then that makes the new our new Kc 1/4 times 10 to the second. It's a really small decimal. 4 times 10 to the -2. There you go. Again, I just want to go over that to get down that concept, but does everyone get that? Cool. I always take your silence as a yes. So if it's, or the one person who decides to say something, thank you. All right, this is something I want to cover conceptual wise, and then we're going to do another ice table. So, and also I realize that this is going long, so remember if you have to go, I'll post the recording, but here's a problem. So we have 2a plus 3b is in equilibrium with C, and the Kp value is 2.5 times 10 to the 9th. So if some gas C is added to the container, please compare the concentrations of A, B, and C. So like is one greater than or less than one another? Like what is this looking like at equilibrium? So one of you like explain this to me. And by compare, I mean like which one is like greater or less than the other. Or if you want, you can type it in the chat. That also works. So, okay, I'll just roll it. So the Kp value is equal to the partial pressure of C over the partial pressure of A squared times the partial pressure of B squared. And we know that that is equal to 2.5 times 10 to the 9th. So something that we need to acknowledge here is that this value is huge. Very big number. So does that mean that this is product favored or reactant favored?
Product.
Product favored, right? And very product favored at that. So if it at equilibrium, if we're product favored, that concentration of C is going to be predominated. It is much greater than everything else. And there's our first part. Now, is the concentration of A or B greater? This is purely a stoichiometry problem at this point.
B is greater
Why is B greater?
because it has a 3 in the coefficient. Or I mean in the
Exactly.
yeah.
Yeah, you're right. And this should be 3. Don't be like me. That should be a 3. But Dylan is exactly right. The concentration of B is going to be greater because for every one C that produces a reagent, one of the reactants, more B is going to be produced than A. But the big concept here is that C is still very predominated because of how favored the products are at equilibrium. So just some more of a conceptual idea for you. If I were to guess, if I were to draw a reaction mechanism for this, it would look kind of like something what we drew on the other page, where no wait, other way around. Sorry, where that forward reaction has just such a small barrier to produce the product, but to get to the product, the reactant, you have a lot of energy you have to put in to achieve that. Okay. Questions? Or I'm gonna scroll. I'm gonna move this down. All right. Let's work on another question here. I'm going to give you guys a second to do this. I don't remember what question we're on, like 5. Okay, so we have the following reaction. 2HI, so hydroiodonic acid is producing, oh no, that's actually what this is. This is gas. It's in equilibrium with H2 and I2. All right, so we have a container with a volume equal to 1.5 liters. And here are some initial things that we're loading it with. So moles of H2 is equal to 0.00623. moles of I2 is equal to 0.00414, and moles of HI is equal to 0.0244. Our temperature is equal to 703 Kelvin. And then it's known that at equilibrium, the concentration of H2 is equal to 0.00467. And I need you guys to tell me, what is Kc? So go ahead and take a second to look into that, and then we will come together and go over it. Just as you guys are working, there's a question in the chat asking if you would get something like this without the equilibrium concentration. No, you would not. You need either the Kc value or the concentration. Or what they could do is they could give you like Kp and then force you to find Kc, but you need one or the other. We'll go over in just a minute. All right, are we ready to go over this?
Yeah.
All right, cool. So first things first, let's find our molarities. So we have our moles and we're given 1.5 liters. So concentration of H2 is equal to 0.00623. Concentration of I2, 0.00414. Concentration of HI is equal to 0.0244 moles per liter. This is equal to 0.0042 molar. This is equal to 0.00276 molar. The last one is equal to 0.0163 molar. Step 2, ice table. So we have 2 HI producing H2 plus I2, IC. So we started with an initial concentration of HI of 0.0163, an initial H2 concentration of 0.0042, and an initial I2 concentration of 0.00276. Our change for HI is minus 2x, and then for H2 and I2, it's plus x and plus x. So then the overall change is 0.0163 minus 2x. 0.0042 plus x is for H2, and then for I2, 0.00276 plus x. Now let's do our Kc expression. So these are all gases, so they're all going to belong in there. So Kc is equal to the concentration of H2 times the concentration of I2 times the concentration of HI squared. Sweet. And we don't know what Kc is equal to. We're solving for that. But we know that the concentration of H2 is equal to 0.0042 plus x, 0.00276 plus x, and 0.0163 minus 2x. Now I know that the concentration of HI is equal to what they give me. H2, I'm sorry. H2 is 0.0047467. So I know 0.00467 molar is equal to x plus 0.0042.
So if you were given a value for H2 and say it was in moles, then you would have to divide by the amount of liters before you can do anything else, right?
Exactly. Yep. It always has to be in concentration. So then I'm going to subtract that over. And that will give you x is equal to 5.16 7 times 10 to the negative 4. So let's solve for Casey. We have 0.0042 plus 5.167 times 10 to the negative 4 times 0.00276 plus 5.167 times 10 to the negative 4. I recommend on the exam that you don't write this all out. Just type it in your calculator if you can handle that. 0.163 minus 2 times 7 times 10 to the negative 4. And then square all of that. So now it's just a matter of plugging this in and plugging it in correctly. And that will give you a KC equal to 0.0663. That is your answer.
So in a problem like that, how would you determine if it's forward or reverse?
So that's a good question. Because I didn't really do that. I see what you're saying. I guess the way that I would look at it is your initial concentration of H2 was 0.0042, and then your final was 0.00467. It increased. If it increased, it proceeded towards the products.
Okay, that makes sense. Thank you.
You're welcome. That's a really good question. So thanks for asking
I have another question. When I set my H2 equal to X plus 0.0042, I got 4.7 to the negative 4 times 10 to the negative 4. I don't know if I'm like doing
It's,
that wrong.
I believe it is because you are rounding the value. So when I say 0.0042, I'm rounding it.
To what?
I honestly, give me 1 second. Because
But I still, my KC value was still 0.0665.
yeah,
It's
like that
just
would be
like it was only
accepted. That's like within the error that they accept.
okay. So
Yeah, the
it's
difference
just a
is like
rounding
when
matter.
yeah, like when you like this value is rounded, it's actually point like 0.004153333. I round it when I write it, but I don't round it in my calculator. Just theoretically that gets you a
Okay.
more exact
Okay.
value.
Yeah.
But the way you did it, I believe they would accept it. They usually have a tolerance that they accept for like questions that you enter in.
Yeah, like the
So,
like past a certain amount of sig figs, like it
yeah,
should be
or
like roughly the same.
like in the key, it'll accept like plus or minus 2% of the actual answer they type it because they know that students may round a little bit differently.
Gotcha. Okay. I was just making sure I didn't.
Yeah, but if you got 0.0665, you'd be good to go.
Okay.
Do we have any other questions how to do ice tables? Because after this, I'm going to move on to chapter 16. There's some important stuff to deal with there. Do you all feel like you can do this? It's the same steps every time, just sometimes the problems may look a little different. Okay. Let's move on to chapter 16. Acids and bases, we're like in the pre-acids and bases era. Few things to go over here. So first of all, This is the general setup that you're going to get when you see acids and bases. They love to ask you to identify acids, bases, conjugate acids, and conjugate bases. So I want to make sure we go over that real quick. So in this first one, remember that an acid is a proton donor, while our base is a proton acceptor. So in this case, this is sulfuric acid. Remember, this is one of our strong acids. Make sure you have those memorized. And this is going to be losing a proton between where it is now and where it is in the product. That is what makes it an acid. This water is going to end up gaining that proton, and that's why it acts as a base. It is a proton acceptor. So the resulting species from this, after it loses its proton, it becomes this conjugate base. When this water gains that proton, it becomes the conjugate acid, which means, and if this were to happen in a reverse direction, this would act like the acid and this would act like the base, where this would be donating, where this would be donating and this would be accepting. And with bases, it's the exact same way. Ammonia is a weak base. And then if it were interacting with water, water here would act like the acid because it is going to donate a proton to the ammonia. Ammonia and ammonium will then act as a conjugate acid because in the reverse direction, it's going to be donating a proton. And the hydroxide ion is going to be the conjugate base. Does everyone understand how you identify those, how you set those up? Does everyone know how to identify them?
Yeah.
Cool. All right. These formulas. So these formulas are not given to you. We'll go over the important trend in a second. You have to have these memorized. These are what we did in class a lot, just going over basic like acid-base like interconversions. And we'll go over an example or two here. So remember that pH to pOH, you can relate them with this formula that they're both equal to 14 at 25 degrees Celsius. Remember that that has to be said. Otherwise, this equation doesn't work at that temperature. To go from the concentration of hydrogen ions to the pH, or to go to the concentration of hydroxide ions to pOH, write it in over here. You're going to use the negative log. Or if you need to go to pH through the concentration of hydrogen, you're going to use 10 to the negative pH. And then to interconvert between hydrogen ions and hydroxide ions, you're going to use the Kw, which is equal to the concentration of hydrogen ions times the concentration of hydroxide ions, which is equal to 1.0 times 10 to the negative 14. There's not a lot for you to do besides just remember these and be able to interconvert between these values. A good way I recommend you practice is you just pick a pH and you calculate H plus, OH minus, and pOH from all of them. Or you can start anywhere that you want and just be able to find the rest of the values, because this is not something that they can make creatively. The one thing to remember with this is that the way a lot of these questions might be phrased is we have an HCl solution with a pH equal to 2.3. So what are the rest of the values? Remember that HCl is a strong acid. What does a strong acid do? It completely dissociates. So all of the HCl becomes H plus and Cl minus. So that means that the entire concentration of HCl becomes H plus. It becomes the acid. So if they were like, what's the concentration of HCl in this solution? Just remember that HCl concentration is equal to H plus concentration because it's a strong acid. That is not the case with weak acids, but we are not there yet. That is not covered on this exam. We will go over that a week from Friday. So I'll actually just do this just to humor you. If I need to find a concentration of H plus, I'm going to do 10 to the negative pH, which is 10 to the negative 2.3. And obviously I'm assuming 25 degrees Celsius here. But this actually works despite that. That's equal to 0.005 molar. Therefore, the concentration of HCl is equal to 0.005 molar. That's simple. Do you have questions about these equations at all? Okay. Here's a big concept that we need to go over. As the strength of an acid increases, its conjugate base strength decreases. And this is something that a lot of students forget, and I'm going to use a few examples to explain this. So first of all, I'm going to take nitric acid. Is nitric acid a strong or a weak acid? I'm going to just shout it out. Okay, so this is a strong acid. If you do not have these memorized, sit down tonight or early tomorrow morning and memorize them. You have to have these memorized. It's one of those things that if you don't do it, you just will continue to struggle throughout the entire course. So this is a strong acid. And as you guys know, this is our conjugate base. Because it is the anion produced from the acid, it will act as a base and if it's going in the reverse direction. So if we go based off this trend, acid strength increases, conjugate base strength decreases. The conjugate base of a strong acid has what we refer to as negligible acidity, which means that in the reverse direction, this barely acts as a base. It's a very stable anion. So, and like a way to think about it is you can like write out the resonance structure. And this is a resonance stabilized. So that makes it a little bit more stable in solution. You don't really have to understand that. But what you do have to understand is this trend that with stronger acids, we're going to see stronger bases. So let's take a weak acid. I like acetic acid. And we're going to produce hydrogen ions and acetate. So this is our acid. This is our conjugate base. So this conjugate base will act like a base. That is why you see this in equilibrium. Because as this acid dissociates in the hydrogen ions and acetate anions, this acetate is going to be reacting with free hydrogen protons or water in solution. And it is going to be going back into this acetate form, into this acetic acid form. It does not completely dissociate. That is why we call it weak. Okay. So the reason why that's important is because a lot of times they'll ask questions and they'll give you, which I'm going to show you in a second, why the understanding of the conjugate is important. Will this produce an acidic or a basic solution? And they're going to give you a salt. You have an entire lab dedicated to this. That, of course, is like weeks away. But it's a complex concept that a lot of people struggle with. But I do believe that she should have covered this in the beginning of the acid and bases unit. So, does that trend make sense to everybody? And it also works for bases too. Like I use I like ammonia. So ammonia is not on your list of strong bases. So it is a weak base, which means that, yeah, so this is the base. So what do we call this? NH4? That's what we call the conjugate acid. And that conjugate acid does act like an acid, and that is what will cause this equilibrium to occur between the base NH3 deprotonating water and the acid ammonium protonating hydroxide. So what do we see this with? So if I asked you all, what will the solution be acidic or basic if we look and we see for a salt PbClO4 If I put that into a solution, will it become acidic or basic? When you get this, here's what you're going to do. Because they like to ask this, it's going to be a big part of lab. So I really want you guys to understand this. This lead, you have a lead cation and a chlorate anion. All right, so cation. Is this cation acting as, is this going to be acidic or basic? That's basically what I'm asking. Or another way to think about it is this a conjugate acid or conjugate base? I want you to think about how these are set up. Like if I took HNO3 versus NaOH, this one always produces a positive cation on dissociation. This one produces a negative anion on dissociation. So when you look at this, I want you to think that lead comes from a base, while the chlorate is coming from an acid. In fact, you can almost think that it comes from PbOH2, is the base, and HClO4 is the acid. Is this HClO4 a strong acid? Yes. So what does that mean about this as a conjugate base? Is it strong, weak, or negligible? Negligible, right. Lead comes from this base that is not on your your list of strong bases, so it is weak. So as a conjugate acid, is this going to be acidic, basic, or is this going to be acidic, or is it going to be negligible? It should be acidic. Therefore, you have a solution that is acidic. Because this is an actively acting acid, and this is a completely negligible base. Does everyone see how we figured that out? Okay. Cool. All right, last kind of concept thing we need to go over here, types of acids and bases. And the real one I want to go over is the Lewis. So the Arrhenius acid, our H plus donor / H plus acceptor. Sorry, give me 1 second. I gotta charge my computer. or yeah. And then Frost-Lowry bases it based off proton. And I should clarify here, this is talking about H plus concentrations in solution. So an acid will increase the H plus concentration in solution while the base will decrease it or increase OH. So those are pretty simple and most people remember those very well. The Lewis is the one that's confusing. So for the acid, we want an electron pair acceptor. For the Lewis base, we want the electron pair donor. And the reason why these confuse people is because a lot of times Lewis acids and bases don't look like normal acids and bases. And the best example, and I'm going to give you the example, ferric bromide. So you all might be thinking there's no way that this is an acid or a base, but this is a Lewis acid. And here's how we know that. If you draw out the Lewis structure of ferric bromide, Fe is attached to Br, Br, Br. That is all it is. The central iron does not have any lone pairs on it. That absence of lone pairs is a big indicator that it can accept an electron pair. So, and that's exactly what it does. If you combine it with a Lewis base, and the example I'm going to use here is Br2. Br2 has a lot of free lone pairs. This can't accept any more electrons, but it can donate them. So what can happen is that those electrons can kind of be accepted by the ferric bromide to produce this. When we're looking at loose bases, another example, good example would be ammonia, NH3. This doesn't really look like sodium hydroxide, but you've seen me use it multiple times. Ammonia has a lone pair on it right here. So if I'm having it interact with water, it can donate this electron pair, in this case with a hydrogen atom, and that can form that NH4. Because it has that electron pair available. But if you get something like one of these metals where they don't have any free electrons, they can't donate electron pairs. This cannot be a Lewis base, but it can be a Lewis acid because it can't accept it. What are the questions on that? So I know that this is typically poorly understood. Or does this make sense to everybody? Cool. Okay. So real quick, we just have a few practice problems here just to go over about very quickly. We're not going to go over the last one just because this is about identifying acids and conjugate bases. I think you guys kind of got the breadth of that. HBr4 is one of your strong acids that we've gone over. See it. There you go. Strontium hydroxide is one of the strong bases that we've talked about. This is going to be a conjugate base because remember it's the cation produced. No, I'm sorry. conjugate acid. It's the cation produced from the base. And then this bromate anion is produced from the strong acid, so it's going to be your conjugate base. Does everyone understand that? I just want to make sure this is such an easy thing for you to understand. And this second one is easy for you to understand too, because we already did a math problem about it. So number one, that's the one I want you guys to try. For this first one, what would this produce an acidic or a basic solution? What are we thinking? See, there's only two of you, so I'm just talking to the two of you. You want to break this up into your ions, right? So you're going to produce CH3 and H3, and that's going to be positively charged, and Br negative. So bromine is a conjugate base because it's an anion, and it's coming from HBr. You should recognize that HBr is a strong acid. So then this has negligible acidity. This is a conjugate acid of some base. So I would say it's going to be CH3NH. Or I don't think this has a charge on it. But this is not a strong base. So this does have some acidity. The solution is acidic. What about the next one? It's kind of the same thing. NaOH, which I kind of wrote into that. So AlNO3 produces Al3 plus and NO3 minus. Negative cation, that's our conjugate base. It came from HNO3, which is a strong acid, therefore negligible acidity. This is a cation that comes from a base, some base, maybe aluminum hydroxide that is not one of your listed strong bases. So then this could be some sort of acidity. So it's acidic. For the last one, sodium chlorite. So that's going to produce a sodium cation and the chlorite anion. So this is from sodium hydroxide, because it's a cation, it's from a base. This is a conjugate acid. This is my base. I know it's a conjugate acid because it's positively charged. This is a strong base. So that means we have negligible acidity. This comes from HClO2, which is not one of your strong acids. It's one of your weak acids. So this is going to have some sort of acidity to it. So the solution this produces will be a base. I'm going to go over one more real quick. NaCl. So we're producing sodium, our conjugate acid, which we just went over, has negligible acidity because it comes from the strong base NaOH, which we know it's a conjugate acid because of that positive charge. The chloride anion is a conjugate base that comes from HCl. And this is going to have negligible acidity because we're coming from the strong acid, hydrochloric acid. Therefore, this solution with NaCl dissolved into it would be neutral. Do we have any questions about that? Well, that's all I really had planned for you guys. I know there's only two of you left in here. Do you either of you have any other questions or like specific problems you wanted to go over?
So like on that, the ones that you just did, do you think that they're gonna give us the table, or are we just gonna have to like figure that out, like where they came from?
The only thing I can assure you that they're going to give you is on your supplemental information. Um, like typically you'll know like where things come from based on if it's a cation and anion. Like cations are typically going to come from bases, and then the anions are going to come from acids. So like you can go off that sense. I can't confirm for you whether or not they'll give you any other information.
Okay, and then one other thing. I don't know if you're allowed to answer this, but like through the grapevine, I've heard they ask us about like colors. Like they'll give you a color of an acid and then be like, okay, well, is it acidic or basic? Like, what do you recommend on that?
I will speak from my experience from my exam when I took Chem 1220 2 years ago. They did ask a question about indicators. Um, just like wanting you, I don't know if they'll put that on your exam this year though. But when I took it, they asked about indicators and like they gave you like a chart and like showed you all these indicators and then told you that they observed a solution with a primarily color with a certain indicator, and then you had to use the chart to figure out what the pH was. I mean, that for me, I just remember it being an easy problem just because you just have to kind of use the chart. It's not really something you can study because you just use like a reference they give you to figure it out. Yeah, with indicators, basically all they do is they give you the indicator, right? So let's say one indicator that I work with in my lab because it's in cell medias is methyl red. Um, Methyl red, I don't even know off the top of my head. It's okay, so it will be red in a pH under 4.4 and and yellow in a pH over 6.2 and then orange in between. So if they were to say that I observed a solution and it's red, what could the pH range be? You would say it's less than 4.4. Like you kind of just have to use just kind of use the references that they give you.
Okay, thank you.
You're welcome. Do you guys have any last questions?
No, but like thanks for holding the review session. It like helped give like a good debrief before the exam.
Good. I'm happy to hear it.
Yep.
Yeah,
In that
thanks so
case,
much. It gives me some reassurance.
good. I hope you guys do well. I hope it helps. I think you guys will be fine. We should have covered like everything that you should expect to see. So hopefully there's nothing out of left field.
All right, cool. Thank you.
No problem. You two have a
Thank
great
you.
night, and I'll see you tomorrow.
Thanks. See ya.